In this lecture, I'm going to talk about Broyden's method, which belongs to a class of methods known as least change second updates. Earlier, I talked about Newton's method, and I mentioned that a significant weakness of that method is need to compute a Jacobian matrix at every iteration. So, assume we have a system of n nonlinear equations. In this particular case, in order to compute Jacobian matrix, we need at least n square partial derivatives of n component functions of our vector-valued function f. And even if we do not have exact formula for computing partial derivatives, we may use finite difference approximation, where h the step and E is unit vector with the only non-zero entry in the kth component. In this particular case, we also do not reduce number of arithmetic operations, and we still have to compute n square partial derivatives. So our goal is to reduce number of arithmetic operations and make our numerical method is more efficient, and as a consequence reduce computational time. So in this lecture I'm going to talk about such method which calls Broyden's method and belongs to a class of so-called quasi-Newton methods. The idea is that we simply replace a Jacobian matrix with approximation matrix which is easy to compute and which finally reduce our number of arithmetic operations. For Broyden's method, number of arithmetic operations will be n squared. So, unfortunately, this approach contains some disadvantages. First of all, we lose the quadratic convergence. As we remember, Newton's method has quadratic convergence, and unfortunately, Broyden's method has just superlinear convergence. What it is? Here is a definition of superlinear convergence. We can say that this is a limit of the ratio between the appropriate norm between the difference I plus 1 iteration and our solution of a nonlinear system, and ith iteration and our solution. And this ratio approaches to 0 as I goes to infinity. In other words, superlinear convergence means convergence faster than linear convergence, but slower than quadratic convergence. At the same time, when we formulated the definition of linear convergence, here was certain number, lambda, we call it lambda constant between 0 and 1, and we call it rate of convergence. So in our case, this lambda is 0. Another disadvantage of quasi-Newton methods is following. These methods are not self-correcting. what it means. It means that, for example, if we deal with Newton's method, iteration by iteration, there is a round of errors, and Newton's method can correct these round of errors from iteration to iteration, and finally we can reach our, let's say, desired accuracy or exact solution. For Broden's method, this is not true, and we cannot eliminate this round of errors and sometimes even achieve convergence without doing some additional steps. Let me describe how Broden's method works. Assume that we want to solve a system of n nonlinear equations. Our general idea of the method is following. First, we choose initial approximation x0. Then we compute next approximation x1 the same way as Newton's method. At this step, when we compute a Jacobian matrix J, we can use exact formulas in order to compute partial derivatives, or we can choose finite difference approximation as I showed on previous slide, formula 1. Then, starting from K2 and all next, actually this is a step where we implement the difference, or so-called Broden's method. Actually, Broden's method, this is simply generalization of the secant method. But if you remember when we mentioned secant method for singular nonlinear equation, we replace our derivative with this quotient. So, and it simplified our calculations. But in our case, when we deal with nonlinear systems, we work in n-dimensional real-valued space, and our difference x1 minus x0 is not number anymore, because here it was just number and this is just number, but this is a vector. So in our case, we replace our Jacobian matrix by matrix A in similar way how we did for singular variable, but here we just deal with vectors. And in order to define unique matrix A, this matrix should follow these two properties, property 1 and property 2, where Z is just vector from n-dimensional real-valued space. Conditions 1 and 2 from previous slide uniquely define matrix A1 as follows. Next, we can compute our vector x using this formula. By performing similar calculations, we can compute vector x for all our k. For example, if k equals 3, here we have a2. This matrix we will replace with a1 because right now in our notation it's a0. We should replace with a1, and this is going to be x3, and this is going to be x2, and so on. In general, if we want to compute vector x at I plus 1 step, we need to use these formulas. These are main formulas of the Broyden's method. And again, just to remind you that matrix A, this is a matrix what we use in place of our Jacobian. And second formula represents our approximation for our vector x. F, this is a vector valued function, what we defined in the beginning. And we introduced a couple more vectors. Vector y, which represents difference between values of our vector valued function f at I and I minus 1 iteration. And vector s, which represents difference between vector x at I and I minus 1 iteration as well. We introduced these vectors just for convenience and just to simplify our formulas. By performing these calculations, what we achieved, we reduced number of functional evaluations from n squared plus n to n. But we still have n cube operations to solve the linear system. And if you remember, we have n by n linear system. In order to reduce number of arithmetic operations significantly, we will use Sherman-Morrison formula. Let's formulate theorem. Suppose that A is a non-singular matrix and that x and y are vectors with a property that product of y transposed inverse matrix A and x doesn't equal to -1. Then sum of matrix A and product vector of vector x and y transposed is non-singular, and the following equality holds. Let's say equality star. What this formula gives us actually? It allows us to compute our inverse matrix at ith iteration from inverse matrix from previous iteration, which means that we avoid computing inverse matrix A directly at every iteration. And as a consequence, this improvement significantly reduces our arithmetic operations. Now, let's recall our formula from previous slide for computing matrix A. This is a formula in the blue box on the right side. Assume that A is our matrix A at I minus 1 iteration. X, this is a ratio. The blue box, it's here. and vector y is Si, which is here. Now let's take inverse matrix from left and right side from formula in the blue box and perform some calculations. Here we apply formula star, and it says us that our inverse matrix A at ith iteration equals to matrix A at I minus 1 iteration, also inverse, minus following ratio. We can simplify this ratio by performing simple calculations. And first we get rid of the denominator and we multiply first our denominator on this term, and then we just perform multiplication, and we can notice that, for example, this product this one is identity matrix and the rest will be just L2 norm. So here we can get rid of this L2 norm as well, and our final expression, let's say 2 stars, gives us expression which shows that our matrix A at ith iteration can be computed from matrix A from I minus 1 iteration. And that's it. This improvement allows us to reduce number of arithmetic operations up to n square. Let's show how Broyden's method works using example. Use Broyden's method with initial guess x0 to approximate the solution to the nonlinear system. This system we already solved in previous lecture using Newton's method. We already defined vector-valued function f, where f1, f2, and f3 are component functions. All of them. We already found a Jacobian matrix, and we will use it here as well. And we already found value of our vector valued function f at x0, and x0 is 0.1, 0.1, and minus 0.1. Now, according to Broyden's method, we should define matrix A in place of Jacobian. And this is how we start. We define A0 as our Jacobian at initial guess. Then we find inverse matrix. At this step, we can use any method, whatever we know. For example, Gaussian elimination. Then we compute vector x for k equals 1. This is simply difference between our initial guess x0 and this product. And all numbers we already computed. Then we can compute our vector valued function f for k equals 1. These are our component functions f1, f2, f3. Now if we recall general formula how to compute inverse matrix A at ith step, we can see that we need some auxiliary vectors. For example, vector y. This is a difference between vector valued function x at first step and 0th step. Vector s we define as difference between vector x at first and 0th step as well. And finally, in denominator, we have this number, and we already can compute it. In order to compute inverse matrix A at first iteration, which means k equals 1, we are going to use formula in a blue box, what we derived based on Sherman-Morrison formula. According to this formula, in order to compute inverse matrix A at first iteration, we need to know matrix A at 0 iteration, also inversed, and a couple auxiliary vectors, S1, Y1. Next line shows how this matrix can be computed, and this is a resulting matrix. Next, what we are going to do is to find next approximation for our vector x. So in our case, it's k equals 2, which is simply difference between values of our vector x at previous iteration, which is k1, and product between matrix A, what we just found, and function f at previous iteration as well. Below there is a table which summarizes results, where k is an iteration, x1, x2, x3 with the components of our vector x, and last column is simply L2 norm. If we recall results from previous lecture where we solved our nonlinear system using Newton's method, we will notice that fifth iteration in Burden's method shows slightly less accurate results than Newton method. But we were able to significantly reduce number of arithmetic operations, and we still were able to achieve desirable result. Finally, let me describe algorithm for Burden's method. Assume that we want to solve system of n nonlinear equations. As an input, we should define number of equations and unknowns. In our case, it's n. Then we should choose initial approximation vector x0. Then we should define tolerance or desired accuracy. And finally, we should define maximum number of iterations, capital N. As an output, we expect to have our approximate solution, vector x, or message that the number of iterations was exceeded, which means that our procedure was unsuccessful. Step 1. Set matrix A0 as a Jacobian, where Jacobian is the matrix of our partial derivatives for each I and j between 1 and n. Then define vector v as our vector valued function f. In this particular case, we have x 0. Then step 2, we define matrix A as our inverse matrix A at 0 iteration. At this step, you can use any method, whatever you know. As an example, Gaussian elimination. Step 3, set auxiliary vectors S, which is in this particular case is S1, then vector X, you update vector X, and this one going to be first iteration, and define K, which will be equal to 2, because 0 and 1 we already computed. In step number 4, we start our loop. While K less or equal than maximum number of iterations n, we should do steps 5 from 5 to 13. Step 5, we define vector W in order to save vector V. When we define vector V as our vector valued function f, where x we take also from kth iteration. When we define vector y, which is going to be also vector y at kth iteration. Step 6, we define vector z, which is going to be our inverse matrix at k minus 1 iteration multiplied on vector y at kth iteration. Then, step 7, we define P, which is going to be number where we have product vector S at kth iteration, our matrix A at k minus 1 iteration, and vector Y at kth iteration. P, just number. When we define vector U as a product vectors S and matrix A, step 9, we compute inverse matrix A at kth step. Step 10, we define vector S, which is going to be this formula where X we take at kth iteration as well. And step 11, we compute vector X at k plus 1 step. This is our final step, step 11. Step 12, we simply check if we achieved desired accuracy or not. And usually tolerance can be, let's say, 10 power minus 3 or 10 power minus 6. And if we achieved this tolerance, we can print our X and stop the procedure. If we did not achieve our accuracy, then we go to step 13, where we assign k as k plus 1. We change our index and go back. If k achieved capital N and we still didn't achieve desired accuracy, we go to step 14 and output that maximum number of iterations exceeded. And then we also stopped, but in this particular case, our procedure was unsuccessful, which means that we didn't find solution.